And it looks like we're live. Well, hi everyone out there. Welcome back to Cambridge University Astronomy. I'm afraid it's a cloudy one this week, so there won't be any stargazing, but we are going to more than make up for it with a fantastic talk from Emma Curtis-Lake, one of the postdoctoral researchers here in Cambridge. And she's going to be talking all about the James Webb Space Telescope and how it's going to revolutionize astronomy. So over to you, Emma.
Thank you so much. Hi, everyone. Thank you for joining us this evening. It's so exciting to talk about this telescope. I'm going to tell you a little bit about why it's important for looking at the very early universe. And actually, we are just over 9 months away from the current launch date. So hopefully, by Halloween this year, JWST, there we go, will be packed up into an Ariane 5 rocket.
À tous des DDO, attention pour le décompte final. 7, 6, 5, 4, 3, 2, 1. Allumage moteur Vulcain. Allumage EAB. Décollage.
And launched into space. I always have to cross my fingers, even when thinking about this. So JWST is too large to fit into an Ariane 5 rocket without being folded up. So once it's released from the rocket, it's actually still got quite a long journey to go, but it's going to start to unfold. The first thing that we see unfolding is the solar panels. And then here we've got a giant sun shield. So this is the size of a tennis court. And it's got to be unfolded, and it's 5 layers of very fine, specially designed fabric that's going to shield the instruments, which are held at the back of the telescope, and the main mirrors. It will shield them from the radiation from the sun and allow these components to cool. So as it's turning around, we're going to see from the face the primary mirror, which is still folded up. And this up here is going to fold down, and that's our secondary mirror. And it all happens at once. There we go. And then we have the full primary mirror. And so light reflects from the primary into the secondary, through here to the back where we have our science instruments. So an update on the status of this project is that by the end of last year, first of all the environmental testing of the full observatory, so this had been done on individual components, but it was only last year that they did it for the full observatory, and that's been completed. And that was where they took the observatory and shook it up, blasted it with sound waves, low frequency sound waves from huge speakers. And this was all to simulate the stresses that it's going to go through during launch. And then after that, they want to make sure that even after all of those stresses in launch, that once they let it go, it can unfold in space. So they tested all of the deployment sequences. And this is what this picture shows. It was the successful deployment and tensioning of this sun shield that was completed in December last year. And you can see there are people down here for scale. And we heard just the other week from colleagues that they've now seen it in its folded configuration. And most of what's left to do is really packing and shipping this amazing observatory. And shipping means literally shipping by boat. So it's currently in California, and it has to make its way to Kourou in French Guiana, where ESA has a space base, and that's where they launched the rocket from. And to make this trip, it's got to travel via the Panama Canal, and it's going to go in its very own custom-made barge. And then, of course, from Kourou is where it gets put in the rocket and sent to space. So the first thing you need to know about the James Webb Space Telescope is that it's big. This is a visual comparison between Hubble, our other much-loved space telescope, and JWST, with some little people here for comparison. Where Hubble has a primary mirror of 2.4 meters in diameter, JWST will have a mirror 6.5 meters. And there's two things that you get from this huge mirror. One is collecting area. So we collect more light, that means we can see fainter objects. And the second is resolving power. And what that means is when you've got two objects that are separate, it's how far apart they can be, and you can tell that they're two separate objects. So with a larger mirror, those two objects can be closer together and you can still tell them apart. And what this translates to is being able to see more detail in galaxies. And I'll show you some pictures to show you what that looks like in a few slides' time. The largest telescope ever in space. It's not yet in space though, so. JWST operates in the infrared. So this is heat wavelengths. If our eyes were sensitive to infrared, then things like a hot cup of tea would look very bright, and our bodies would look very bright to our eyes. So these things are going to look bright to JWST. In fact, Hubble looked a little bit into the near infrared. And we had another space telescope which looked in the infrared, and that's the Spitzer Space Telescope. But the other thing that's shown in this is the size of the mirror again, so that collecting area. And Spitzer had a really small mirror, so it was amazing, and it did tons of really cool science with it, but it wasn't very sensitive. And it also didn't have great resolving power. So here's an image from Spitzer. This is what we expect to see with JWST. So I'm going to take you, first of all, have a look at these two objects. Here you can definitely tell there's two different objects, right? And let's go back to Spitzer. No way can you tell. Then I'm going to take you to this object here. This one, this is about the collecting area. This one's quite faint. And with Spitzer, it was too faint to be observed, right? So we get two things. We get to see the fainter objects and we get to see them in greater detail. So JWST's orbit will be really far away from Earth. It will be at the second Lagrange point. And you can see that in this diagram here. What that means is, once it's there, in its orbit around the sun, it's going to orbit at the same rate as the Earth. The Earth will always be between JWST and the sun. And this means two things. First off, it's really far away from the Earth. So whereas Hubble was in quite low orbit, Webb will be 4 times the distance between the Moon and the Earth away. So much, much further away from the heat that the Earth is radiating, because it wants to look in those wavelengths. And so it needs to be away from sources of heat. And the other thing that it gets, because of that orbit, is it means that it can always orient this sun shield at the Earth and the sun, shielding this part of the telescope, which means that the mirror will be operating at 50 Kelvin. So that's minus 223 degrees Celsius. And the instruments, most of them, in fact, passively cooled to just a little below that, 39 Kelvin, and one of the instruments requires cryogenic cooling down to 7 Kelvin, which is minus 266 degrees Celsius. So there are 4 instruments on board, and this has been a really, truly international effort. 3 of them are looking in the near infrared from 0.7, sort of just in the yellow end of the visible spectrum, to 5 microns. We have NIRCam, that's the near infrared camera, so predominantly imaging. It does have some spectroscopic capabilities, and this was built in Arizona. NIRSpec, near infrared spectrograph, spectroscopic capabilities, was developed by ESA, the European Space Agency. NIRISS FGS, this was originally the guiding system, but also has some spectroscopic and imaging capabilities. That was provided by the Canadian Space Agency. And MIRI, which takes us from 5 microns all the way to 28.5 microns with imaging and spectroscopy. MIRI, the mid-infrared instrument, That was built for ESA by a European consortium in partnership with NASA's Jet Propulsion Lab. But in fact, components of it were built at UKATC in Edinburgh, and I believe parts in Rutherford Appleton Laboratory as well, which is near Oxford. So really parts that have been put into space have been built in the UK. In terms of near spec, this is kind of one of my favorite instruments. I'm very heavily involved in the team that's working on it. We're able, for the first time in space, to take clean spectra of many different objects at once. So I'm going to explain to you why these are important, but spectra is just when we split up the light, and it's like when you have a prism and you can see the different colors. And we've been able to do this from the ground for a long time. We call it multi-object spectroscopy, but often those systems have involved a kind of robot where you move a component to a certain place to be able to pick off the light from the galaxy that you want to see. But that type of a thing might, if they get into trouble or tangled, we can't sort it out from the ground because it was too with me in space. So they solved this by creating an array of tiny, tiny shutters. So there are only 250,000 shutters, 200 microns wide. That's like the width of a human hair. And then we can open and close them independently. So we can open them when we want to let through the light from an individual galaxy. And this image here is actually created with the MSA. So this was done with by colleagues in the States, and they were doing some testing at a point when there was a really terrible storm coming over, and they actually took the satellite image of the storm. And where it's light, the shutters are open, and where it's dark, they are closed. So when the shutters are open, they let through light, and we get a spectrum. So the light is split up from the object. And I'm going to explain to you later why this is important. So to recap the important things about JWST, it is big, the biggest telescope to go to space. It observes in the infrared, and it will take spectra. Why are these things important? So I'm going to tell you about why we need these things in particular for looking at the very early universe and the first galaxies. And to do that, I'm going to give you a brief history of the whole universe in a single slide. After the Big Bang, the universe is hot, and it's expanding and it's cooling. And it's only once the universe gets cool enough that individual protons and electrons can join together to form neutral hydrogen and helium. It's only at that point that light can travel in a straight line, because in fact, light gets scattered by charged particles. What this means is we can't see further back in time than this point here. We call it the last scattering surface, or you might know it by the cosmic microwave background. And it's from this point onwards that we have a cool universe. It's got neutral hydrogen, helium, trace element lithium, but it's dark. And gravity is doing its job of pulling matter towards each other. But it's only once you get to a point where there's enough matter in a single place that it gets dense enough and hot enough to ignite hydrogen fusion that we have our first stars. And those stars will be built up just from the building blocks left over from the Big Bang. There's still a lot of neutral hydrogen in the universe, and it takes a while for the stars and the first galaxies to ionize that again. So that means that a proton and electron that makes a neutral hydrogen, they get broken apart, because by the present day, most of the hydrogen in the universe is ionized. And in fact, most of that, we call that the epoch of reionization, and that is mostly finished by about 1 billion years after the Big Bang. So this is a different slide that kind of zooms in on this epoch I'm talking about, when the hydrogen in the universe has gone from being neutral to being reionized. We have the dark ages, we have the first stars, the first galaxies, and remarkably, Hubble has detected galaxies well into the epoch of reionization. I'll explain to you how that's possible, but I'm also going to explain why it is that Hubble cannot see any further back in time than this. And this is not to do with how faint they might be, but something else entirely. So we're looking back in time, right? And the reason we can do this is from the simple fact that the speed of light is finite. So I love this animation. It shows in real time the time it takes for light to travel from the Earth to the moon. It takes 1.25 seconds. So that means that we're seeing the moon 1.25 seconds ago. It takes 7 minutes for light to reach us from the sun. So we're seeing the sun 7 minutes ago. And so the further away an object is, the further back in time we are seeing it. So really, we can probe to earlier stages of the universe by putting a telescope on a patch of sky and staring at it for a really long time. But back to the question of why we can't see any further with Hubble, even if we were to stare longer. And there's 3 concepts. You may already know them, but I'm going to go through them and bring them all together. So the first one is the Doppler effect. You may be familiar with the explanation of when an ambulance siren goes past and the pitch changes. Well, this is a different representation. I really like this one. So we've just got a dot, and let's say it's emitting a circle that's expanding. When it emits that circle, it's in the center of the circle. But by the time it emits another one, it's moved. And that means that in the direction of motion, these circles are going to be closer together. And behind it, they are spread out, they're further apart. And when we think of light, what we think of is that each of these circles is like a peak in a wave. And when they're spread out, that means that the wavelength is longer, and that means it's shifted into the red. When they're pushed together, that's shorter and it's shifted into the blue. So when it's moving away from us, the light, we call it redshifted, and we can tell how fast something is moving by the amount that light has been redshifted. The second thing, Edwin Hubble showed us that the further an object is away from us, the faster it is moving. So that means that if we can get a velocity or a speed measurement, that gives us a distance measurement. So the more redshifted something is, the faster it's moving away from us, and the further away from us it is. So put these 2 things together, and we know that because of the finite speed of light, the further away we look as well, the further away we're looking back in time. However, there's something that's also blocking some of the light from those early galaxies, and that's that neutral hydrogen that I was telling you about. So they get in the way. So when a photon, a particle of light, interacts with a neutral hydrogen atom, if it has enough energy, it can give some of that energy to the electron. The photon will be scattered off it, and the electron will leave, just leaving the proton or the hydrogen nucleus behind. If we look at that in closer detail, the photon is kicking away that electron, but it's lost some of its energy. And when we're thinking of a photon's energy, that is directly linked to its wavelength. If it gives away some of its energy, that means that what's left, it will be a photon with a longer wavelength. So it will no longer be in the part of the spectrum where it was to be emitted from. it's redistributed. And if it's exactly the right energy, then it's lost altogether. So what does that mean for galaxies and what they look like? So there's quite a lot in this slide, and I'm going to take you through it quite slowly. When we take images of a galaxy, we do so by using filters to pick off parts of the spectrum. So each of these is a filter, and it corresponds to an image at the bottom. So these are HST filters, and this here is our Redshift 3 galaxy. And as I'm going to redshift that galaxy, so I'm going to push it further away from us in the universe. And as it gets further away, you'll see that it's starting to lose flux here. It's changing. Nothing is changing necessarily on this side, but we say on the blue side, we're losing flux. And that's because those photons from that part of the spectrum are meeting neutral hydrogen along the way. So I'm going to play that again. What that means in the images is that beyond a certain wavelength, we see nothing. So there's kind of two things going on as to when it disappears. There's when there's not enough photons from the galaxy in the first place, and then when the photons from the galaxy itself are meeting neutral hydrogen. But both of those things together mean that once we get to redshift beyond sort of 12, we're running out of space with Hubble. And as soon as it's out of this filter, we won't see it anymore. So it doesn't matter how bright it is, at a higher redshift, we just cannot see it with Hubble. This means that not only is it a further way to look back in time, it means that to look back in time, we also have to look at longer wavelengths. And to probe the really high redshift universe, HST has run out and we need JWST. So it's not just about detecting these galaxies, actually. We care about more than just that. That's only a very small part of the science goal. For the first time ever, we're going to get spectra of thousands of galaxies in the early universe. And why is that important? When we split up the light, we get fingerprints of different elements that are present in the galaxies. So the first galaxies, we would expect them to only have the fingerprint from hydrogen and helium. And then as they process the primordial elements into heavier elements, like carbon, like nitrogen, like oxygen that we breathe, we'll start to see the imprints in the spectra. So thinking about different elements that are important to us, the iron in our blood, in the hemoglobin that transports oxygen around our body, that cannot even be made by nuclear fusion within stars. That requires a much more energetic process. And in fact, most of the iron that's in your blood was created in supernovae out in the universe. And it's from tracking the buildup of elements over time that we can start to understand where they were built in the universe, what objects made them. And I'm going to show you a really busy figure now. I love it. I think it's amazing. So this is the periodic table, color-coded by when and where certain elements have been built in the universe. This is made by Chiaki Kobayashi, and it's from simulation. This is theoretical. This is not observed. So each of these has like an x-axis, which is time. So as time progresses, the amount of an element builds up. So at the beginning, just after the Big Bang, we just had hydrogen, helium, lithium. There was no iron, there's no carbon, oxygen. And it takes time to build up these elements. And they're built up and produced in different places in the universe. So I told you about iron predominantly being made in supernovae. So the blue is from core collapse supernovae, where a star collapses in on itself, and type 1a supernovae, where it's had a companion and it accretes matter from the companion to a point where it starts to collapse and then explodes. So by looking at the buildup of different metals over time, we can understand what objects are making these metals and their buildup. And we can start to test these types of simulations, which may not be correct. So it's not just about the redshift frontier. We get spectra for the first time from thousands of galaxies at this epoch, and this is what's going to be truly transformational. We'll get accurate redshift, so we'll know the distance away from us. We can search for signatures of the first stars or primordial black holes, so they're the ones which only have the fingerprints from hydrogen and helium. But beyond that, we can look at how stars and galaxies process and transform those primordial building blocks into the elements we see in our galaxy, in our solar system, in our planet, in our bodies. And with that, I'll finish, and I'm happy to take questions.
Wonderful. Thank you so much. Absolutely fascinating talk. I have to imagine a virtual round of applause. I love that figure of the periodic table with all the elements like changing over time. That's so cool. I feel like you could just spend hours kind of like lost in all the details.
In fact, I just put it back on because it's like, okay, we'll leave it on that one.
Okay, so there have been lots of questions coming through already. Anyone that has a question for our speaker, just pop it down there in the YouTube chat. In the corner. I'll do my best to get to it. So first question, if you don't mind, from Martin, who wants to know, why don't we just put the JWST in Earth orbit first to make sure it works properly and then send it out to L2?
Oh, I love that idea. I suspect, but I'm not sure. I suspect it requires a certain trajectory such that it doesn't need too much extra energy to make its journey to L2. So if you actually put it into orbit around Earth, it needs a lot more energy to get it out of orbit again.
Question from Daniel, something that astronomers have been asking ourselves quite a lot over the last few years. Why did it take so long to launch James Webb, and what caused the delay?
Oh, well, I think many factors have caused the delay. There was a fun issue with the sun shield, where in the last delay there was some environmental testing where they shake it up, and I believe some of the bolts came loose, and we don't want that to happen in launch. So they had to redo quite a lot and rethink slightly the design. So it was a good thing to have been delayed because it was something that could be rectified before launch, basically.
A follow-up for that. Someone also wants to know, looking into your crystal ball, what do you think James Webb will actually launch this October?
October, well, it's already set for the 31st of October. So any small shift, it may well head out of October. The schedule is looking good because they do still have quite a lot of buffer zone there. So I'm hopeful, but then I can't say more than that.
No, but yeah, I think we all have our fingers very firmly crossed. Question from Wakefield Astronomy wants to know something that actually the speaker and I were talking about before the talk. Do they have a backup telescope in case something goes wrong after launch?
No. So parts of the run to make JWST were bespoke. And so there was like a single production run, and then everything that was needed to produce it was reallocated. And so they didn't make two of everything as they were going along. So no, there isn't a second JWST. There are other amazing space telescopes to be launched in the future. So if you're interested in that, there's the Nancy Grace Roman Space Telescope, which is also pretty awesome, but no second JWST.
And so I guess following on from that, talking about exciting future projects, I know there's this, I never know how to pronounce it, Le Voir or something, which is the successor to James Webb, maybe launching sometime around 2040. Raj wants to know, how long is JWST going to last? And do you think it might work in concert with future space telescopes? Like what's the expected lifetime of a mission like this?
We're hoping 10 years. It could be shorter. But it could be longer. I can't remember what the limiting factor is, but the hope is for a 10-year lifespan, and that would hope. There's a telescope going up next year called Euclid, so we should have large overlap with that, and we're hoping for, I hope there'll be overlap as well with Nancy Roman, the Roman Space Telescope. But it's not a long term mission.
So a question from Laura, what is going to happen to Hubble when James Webb becomes operational? Is it going to get decommissioned and become space junk, or what's the plan?
Yeah, I don't know the plan. I'm always surprised when there's another call for proposals coming around. I always expect it to be the last call. I don't know what they're planning to do with it. I've heard rumors, but I wouldn't want to propagate the rumors because I suspect they're not true.
Okay, question from Eva. What is the James Webb Space Telescope going to tell us about dark energy?
Ooh, that's such a good question. It's not designed specifically for dark energy. So the reason why it's not perfect for that is because it's good at looking at a small patch of sky for really deeply, so seeing really far away. But for dark energy, you want a wider range. So the best constraints probably that JWST will provide will be from observing supernovae and being able to calibrate them better. But it was not designed as a dark energy mission.
Okay, question from Gongman wants to know why French Guiana? Like, what's so good about launching from there?
So it's ESA for a start. So it's previously French territory, but also I believe you need to be quite close to the equator for an efficient launch. But beyond that, I can't give more details.
Okay, and a question from Gaurav, and I think this is something that luckily you are an absolute expert in. How will James Webb enhance our understanding of the formation of galaxies and things like that in the early universe?
Yeah, so at the moment in the early universe, we really just have some images from Hubble. And the amount that we can tell about these objects is quite limited. We can tell that they're forming stars. And some of them we even have a redshift for. So we can tell that they're at the redshift we think they are, and they're not some low redshift object that's an interloper. And from that, we've been able to learn some useful things. We can learn about the counts of them and the populations of them as a whole, but we can't really learn about what metals are in them. And we haven't been able to tell, how much mass in stars there is. We have some idea thanks to Spitzer, but they're really uncertain. And both the spectroscopy and the imaging are going to allow us to better characterize their physical properties. So how many stars they have, what metals there are, and also sort of like what they were doing in the past. So we might hope that we might be able to tell if some of them were really bursty in their star formation. So, maybe they had some peaks, or whether they were just bobbing along smoothly. So these are the type of things that we're going to learn and that we have no idea of at the moment.
Fantastic. So just a follow-on question from Paul then. So James Webb is obviously going to be very good at studying these galaxies. Is it going to be able to tell us anything about exoplanets?
Oh, tons, but I know nothing about that. I really hope that you'll have another talk from someone who knows about that. Yes, it's another core a core science goal of JWST, because it's observing in the infrared. It's a better contrast between the star and the exoplanets, so you can get direct imaging of them. And the spectroscopy as well should allow you to get information about the exoplanet atmospheres and things like this. So yeah, it's going to be amazing for exoplanets. And they've actually taken the first set of proposals, so asking astronomers to say, what do you want to look at? And it was split, quarter of those proposals for the time was for exoplanets, quarter of that was for galaxies. So it's as big a component.
Excellent, thank you. And so I guess we'll make this the last question so we don't keep you talking all night. A question from Richard, who wants to know, do you about the projects that you yourself going to be involved in once James Webb goes up?
So I'm part of what we call a GTO team, a Guaranteed Time Observation team for near-spec instruments. And that means there's usually a team of scientists that are really involved in the process very early on to help engineers design the instrument. And the payback of that is that they get time on the observatory when it goes up. So as part of that team, we're designing a survey to look in a couple of fields where HST has stared at them for hours and hours and hours. In fact, including the Hubble Ultra Deep Field, we'll be looking at that with NearCam and NearSpec. So yeah.
Wonderful. Well, thank you so much to everyone listening. Hope you enjoyed it. Thank you so much to our headline speaker, Dr. Emma Curtis-Lake, for that fantastic talk. I think pretty much every astronomer in the world is very eagerly anticipating this autumn to see something very exciting happen. So that's all for tonight. If you've enjoyed it, please consider giving us a subscribe. We have these videos, these talks going out every single week, and we have lots of really exciting stuff coming up at the end of March for the Cambridge Festival. Join us again next week, so 7:15 next Wednesday, where we're going to have a talk all about the life and times of binary supermassive black holes. So yeah, see you next week. And we're done.
Thank you.